Welcome back, everyone. Let me introduce today's speaker, Ferenc Karsai. Ferenc joined VASP after a postdoc with Peter Blaha around the same time that VASP became a company in 2017. He is a theoretical chemist by training and an expert in many areas that VASP can be applied in. For instance, electron-phonon coupling, core excitations, and MD in general. But his main focus as a developer is machine learning force fields. Therefore, I'm very pleased that he takes the time to present a general introduction to machine learning force fields today. So, Ferenc, the stage is yours.
Thank you for the nice introduction, Marie-Therese. As you told, I'm going to tell you about the machine learning force fields in VASP, and let me directly jump into the talk. Okay, so density functional theory, as shown here on top with its Kohn-Sham equations, has been the workhorse for computational solid-state physics and chemistry since many decades. It is quasi ab initio, despite a few parameters maybe. It's reasonably fast, and it's reasonably accurate. But unfortunately, if going to finite temperature, that means mainly the motion of atoms by molecular dynamics, it is too slow. Let me take an example. 100,000 time steps, which often belong to only a few picoseconds, we could easily take up several months to simulate. Additionally, this is only on small to medium-sized unit cells with around only 2,000 electrons at maximum. So for that, there have been many classical workarounds, like cluster expansion, coarse graining, and probably the most famous is force fields, to which we come here. So classically, force fields have a physically intuitive and at the same time computationally inexpensive form. Famous examples are, for example, the Lennard-Jones potential and the Axelrod-Taylor potential. They are computationally inexpensive with very few parameters only. With them, typically one can go up to even millions of atoms for several microseconds or even more. But of course, this comes at the price that it captures very limited accuracy in physics. So another type or a further improvement of these force fields are so-called parameterized force fields. This is done by parameterizing them to many DFT calculations. With this, the accuracy, of course, can be hugely improved, but mostly the accuracy is still not good enough compared to DFT. Also, the big point of this, the big problem of this, is that making these force fields is very cumbersome, and it can easily take several months to make a decent one. So what do we need? We need a force field that retains the accuracy of DFT, but is approaching the classical force field in terms of efficiency. And this is machine learning, or we could say the new sledgehammer, if we want to say, which, depending on the training, of course, comes very close to DFT. But at the same time, the execution time is more or less close to the parameterized force fields, not to the very simple, but to the parameterized, more complex force fields. Another strong point is also of these force fields that are very easy to make compared to the parameterized force fields, because they need really low to no human intervention. So here you can see the efficiency of the machine learning force fields from bottom to top. Here. In principle, the accuracy with respect to experimental data would go vice versa, but the machine learning force fields are very close in accuracy to the underlying system. So if we would, for example, have as an underlying system some RPA calculations which are beyond DFT, then the density functional theory would be more closer to RPA. That means better than DFT. So the vice versa trend is not given here. But going back to efficiencies, we see that DFT needs around seconds to hours, depending on the computational parameters, of course, and the size of the system. And our machine learning force fields need around milliseconds, few milliseconds. So this is the speed per atom per core. This means that at least the machine learning force fields are 3 to 4 orders of magnitude faster than DFT calculation. So in the example I mentioned before, the DFT with 100,000 time steps, that would need several months. It actually needs now with the force fields few hours. As a side note, classical force fields will and always are and will be, due to their really simple forms, faster than machine learning force fields. But we're approaching them every year. Okay, after this introduction, let me talk about force fields, and here I start with the basic ingredients of machine learning force fields. First of all, you need a set of reference calculations. For example, this can be a set of single-point ab initio calculations or a set of snapshots taken from an MD by ab initio. The reference calculation set consists of multiple structures. Each structure consists of the ion positions and the lattice vectors. It also contains the energies, forces, and stresses from ab initio. The idea of machine learning now is to learn a force field or make an algorithm in which we learn how to get from ion positions and lattice vectors to energies, forces, and stresses without actually performing the ab initio calculations. The basis for this is the reference dataset here. VASP, just to mention, VASP offers here specialty, which is on-the-fly training, but I will talk about this later. The other two ingredients are now concerning the inner workings of the machine learning force field itself. One is that a machine learning force field needs a good representation of local environments, but we will discuss this in more detail. But for now, let me just note that we cannot use the Cartesian coordinates. They do not incorporate the symmetries like rotational invariance. This is here, this was. And the last ingredient is the actual machine learning algorithm, which must be a method that can reproduce complex functions, in our case, the potential energy, given a high dimensional input, the descriptors, to which I will come next. There are many algorithms out there. The most famous are probably neural networks and kernel-ridge, and VASP uses kernel-ridge regression. Yeah. Okay, let's go into more details of VASP machine learning force fields. The key assumption of many machine learning force fields is to write the potential energy as a sum of atomic energies. Note that there is no physical justification for this, and DFT will not give you per atom energies. Then the per atom energy contributions are the outputs of a machine learning algorithm. The inputs are the local environments. That is the positions of the neighboring atoms. In our case, we use a cutoff. So neighbors within a certain cutoff radius are only relevant. And here now comes a crucial point. What would happen if we would use the Cartesian coordinates directly as input for the machine learning functions? It would not know automatically anything about translational rotational invariance. For that, we would have to provide this information in the training data set. That would mean we would need a huge training set, making the method really impractical. So in order to avoid this, we insert the so-called descriptors between the coordinates and the energy forces and stresses. These descriptors should take the variances into account. They will transform the neighbor ion positions relative to a central atom usually. And these are then ultimately invariant with respect to translations and rotations. So these descriptors will be the input in a machine learning function. So let's talk about this atomic ion environments or descriptors. since the beginning of these types of machine learnings, what I have shown before, there have been many proposals here. I just wanted to list some of them for the interested listener, but I don't want to start a comparison between them here. I will focus on the one used in VASP. So the basic idea is to expand the atomic density distribution around each atom. Unfortunately, the distribution, rho, is invariant under translations, but not with respect to rotations. So we need some kind of variation or approximation that introduce also rotational invariance. These are pair and angular correlation functions. Here, these two. I will also call them sometimes pair descriptor, angular descriptor, two-body descriptor, three-body descriptor. So sorry if I mixed them up, but we have many names for them. So the first one is this pair correlation function here. So this measures the distance r between an atom I and so central atom I and its neighbor atoms j, involving only two bodies. Then next we have the angular correlation function here. This measures the distance to a central atom I of an atom j and k with distances r and s, and the angle between them. So this descriptor is essentially a three-body descriptor. It is also noteworthy that if the two distances r and s are the same in the three-body descriptor and the angle is 0 between these two atoms would lie on top of each other, and in principle this would then contain the two-body descriptor. This. So now we see how these descriptors are constructed. First, we expand the density distribution in a two-body auxiliary basis C with indices I and Lm. I will call them C and Lm since the central atom I is more or less implicit in the rest, because we always need it. These C and Lms are then expanded into radial basis chi and spherical harmonics. For the radial basis in VASP, we use modified Bessel functions. So these auxiliary functions are the coefficients then of the pair. So here and here, three-body functions. For the pair descriptors, we take them directly, and for the angular descriptors, we take the product of this. Typically, we have much more angular descriptors than radial descriptors. The number of angular descriptors is between 400 and 2000 usually, while the number of radial descriptors is between 8 to 12. So now we come from the descriptors to the fitting problem. We start by asking the question, how should the function for the energy contributions U look like? Yes, actually one way of tackling the problem is to use a neural network where input nodes are descriptor values and the output is the energy contribution U. However, in VASP we follow a different path. Let's assume we would try a standard regression method. So we represent our function U as a product of weights and some basis functions phi. Then in just a simple 2D example, we need a complete set of functions like written here. So with the complete set of all combinations of x, y, and their powers. So this would also mean we need to construct a complete set of functions in 1000+ dimensions. This is of course not feasible, so we have to come up with a solution. And one solution is the so-called kernel trick. So instead of a huge set of functions, we build a kernel that allows us to compare the current environment of interest to previously determined environment, so current environment X to previously determined environment XIB within this kernel functions K here. So the kernel should be nonlinear function that measures the similarity between X and XIB. In VASP, we employ polynomial kernels. This builds the dot product between XIB and XI. And then this product is raised to the power of Xi. Yep. So this means when the two vectors are orthogonal to each other, or in other words, are not similar, the dot product becomes 0. Otherwise, if they are fully similar and we use normalized vectors, the dot product becomes 1 or approaches 1. Another good thing of this kernel is that we have determined that Xi equals 4 is more or less universally good. So we don't have to worry about any parameter anymore in this kernel. Another example would be Gaussian kernels here. As you can see, this just measures the distance of two vectors xi and xib and then puts a Gaussian on them. So when the environment's identical, the kernel is 1 because so x minus xib is 0 then, and e to the power of 0 is 1. Otherwise, if the two descriptors are different, the Gaussian approaches 0. So let's visualize a fitting procedure on a very simple example using this Gaussian kernel. And we do this for the total energy U here. So in green or blue, we have here the unknown observable. This is our function, or target function. Then we use here, as you see, a one-dimensional descriptor. We have 5 reference points where we know the exact value of the function. And now what this kernel does, we put a Gaussian on each of these reference points here. And this Gaussian has equal heights. Now by doing the fitting, what you see is that we get different weights of these points. So each Gaussian changes its height. It has a different height. And with these Gaussians, then if we plot the new function with this, we see that we can nicely predict this function or approximate this function with these 5 values. Okay, and now let's come to the actual fitting problem itself. In principle, we have to solve a simple least squares problem as seen on the top here. In that equation, this phi is a so-called design matrix. It contains the kernels and the derivatives of the kernels for each central atom. It also connects the weights with the target vector y. So let's talk about the dimensions of this matrix. In one dimension, and so in the first dimension, design matrix contains all energies, forces, and stresses for each structure. Let's take an example. For example, for 500 training structures and 100 atoms in each training structure, that would be 500 entries for the energies, 500 times 100 times 3 because of the 3 Cartesian interactions for the forces. And this is also the same dimension as y has, so as y with the reference energy, so training energies and forces and stresses, of course. The other dimension of this design matrix, the columns, contain the number of local reference configurations. This is also the number of weights we have in the system. So if we assume 500 local configurations and take the previously approximated 150,000 lines for the energies, forces, and stresses, we end up with a hugely overdetermined system of 500 unknowns and 150,000 equations for them. So this suggests that we need some kind of regularization. And with that, we come to the employed methods in VASP. So we use a method using this regularization called Bayesian linear regression. Here, we solve this equation by LU factorization to avoid this kind of inversion, because the inversion would make the condition of the problem worse. Here is the regularization, what I mentioned before. The product of these two numbers, this doesn't matter, this is just a detail. It's one number, more or less. And it also, now the problem is, now it also involves the squaring of this matrix, or the product of phi transpose times phi. Squaring means we also square the condition number. And the high condition number means worsened accuracy. But solving this by LU factorization is a fast method. So solving this equation in this way. And this is what we employ during training data acquisition, where we have to do many fittings. The other method which we employ is the more exact way, is by using this pseudo inverse. So here's first to make a singular value decomposition of this sigma, of this phi, sorry, and by rearranging cleverly the components of the singular value decomposition and using W and Y, we get to the weights this way. The nice thing is that this does not require any squaring of the design matrix. And this results, of course, in a much better conditioning than in Bayesian linear regression. This, of course, as I told you, the better conditioning results in a higher accuracy. And this accuracy can be substantial sometimes. It can be up to 30 to 40% in some systems. Yeah, another nice thing is that we can also involve regularization here by regularizing these singular values with this here. The drawback of this method, of course, that is computationally much more expensive since we have to do a singular value decomposition. Hence, we only use it once at the very end of the training, where we refit the data and obtain the final force field. So with that, I want to wrap up what you heard until now about the employed methods in VASP. So the total energy is the sum of atomic energies. These atomic energies are the sum of weighted kernels. We have two ways of fitting: the less accurate but fast Bayesian linear regression, which is used for data acquisition, and the more accurate but slow pseudo-inverse using SVD, which is only used once in a refitting. Next, kernels measure the similarity between a target atom I and the local reference configuration IB. VASP employs for this polynomial kernel. The descriptor xi describes local environments of an atom I up to a cutoff radius, and xi also contains 2 and 3 body descriptors, which are invariant with respect to translations and rotations. So now we come to the point where we have established the methodology to represent and fit the database, but we haven't acquired any data until now. So our kernel-based machinery requires 2 data sets. Start with the left. Here we have the so-called training data set. It consists of the structural data, that means ion positions and Bravais lattice, and these are which are required to construct the descriptors. And also it consists of the energies, forces, and stresses belonging to each of the structures, and these are required for the fitting. On the right-hand side, we have the local reference configurations. These are specific to the kernel method. They are the environments used as reference configurations to construct the kernels, as you have seen before. And they are also saved as descriptors. And they are usually chosen from amongst in the training data. So now that we know what we need, there are two questions. One is, how do we create the training database? And the second is, how are the local reference configurations extracted from the training data? And let's start with the brute force approach. This would be to run an ab initio simulation and extract the data from that. That would mean we run an MD for 100,000 steps and extract the structure, let's say, at every 1,000 step or whatever. The idea would be to possibly cover a large phase space. But as already mentioned in the beginning of this talk, this would be computationally very expensive and could take up easily several months. Additionally, since we only take every whatever thousands or nth calculation, the rest would be useless or thrown away. So why not already select the data right? So select only the right structures for ab initio calculations in advance. This could be, for example, attempted by Monte Carlo sampling. But the problem is here we would most likely have the problem that we doesn't go to the right phase spaces in MD calculations. Also, still in both, we have the problem how many to choose to have a desired accuracy. So to sum up, what we need for a good sampling is it has to go over a long trajectory, it has to go over the right trajectory, it has to go with the right phase space, and it has to perform ab initio calculations only if necessary. The solution for this, as you may have saw this, I've mentioned already, is on-the-fly learning, or sometimes, or also called active learning. So this can be mixed up, these two. So let's have a look on the on-the-fly learning algorithm in VASP. So we start by checking if we have machine learning force field or not already available. So if we start from scratch or have a continuation run. After that, we set a molecular dynamics calculation with a given length. The whole thing here will be done within this molecular dynamics calculation and run until the end. Within that calculation, the following steps are then carried out. First, we predict the potential energy surface. That means energies, forces, and stresses by the force field, and predict their uncertainty using the Bayes theorem and using the variance of the forces predicted with this Bayes theorem here as the uncertainty estimator. Then this prediction is compared to some threshold. The threshold can be either automatically updated or set constant as a target value. And from this point on, two branches will emerge. Let's start with the left one. So with the yes, that means the error is above this given threshold. In that case, if it is above, we have to do a first principles calculation. Add the energies, forces, stresses, and the structural data to the data set, and choose local reference configurations, and possibly retrain or not. What do I mean with this possibly retrain? Is the retraining is not done at every step, but usually after a block of data is filled with new training data. By default, this is 5 in VASP, and this is to minimize computational overhead. After that step, we come to the next step of the molecular dynamics, and an update of the positions is done. So the alternative route would be that there's no, so this error is smaller than the threshold. This would mean the force field is accurate enough, So this means it comes directly to the update of the next positions and goes back to this step here. So if in principle, if you do this on the fly learning, then you would see that with evolving time, less and less times you encounter this yes pass here, since the force field becomes better and better. And ultimately, on the whole length of like a 50 to 100 picosecond trajectory, the algorithm skips around more than 99% of the ab initio calculations. And the other nice thing is that the whole algorithm is fully automatic, and you need to only control it, but don't need any other human intervention. So let's have a look here at the Bayesian error estimator in a practical calculation. Here on the right, you see solid silicon heated from almost 0 Kelvin to 800 Kelvin. That means why 0 Kelvin, almost 0 Kelvin, because you should never set 0K in VASP. This is just a side note. On the x-axis, you see the time steps. We had 20,000 time steps. This is a more relatively short on-the-fly calculation. You need possibly around 50 to 100,000 time steps, around 100 to 200 picoseconds, that would mean. And on the y-axis, you have the error in forces. So now let's have a look at the curves. So the red curve here is the average fitted error. That means error from ab initio calculations versus the predicted values. These are the true errors. You can see from the steps that this is only updated if the force field is refit. So the force field is freshly fit, more or less, at every step. The green curve shows the Bayesian errors. These are updated at every step, or calculated at every step. And the blue values are the thresholds for the learning. Here, the thresholds are calculated as the mean of the Bayesian error for the last 10 steps where ab initio calculations were carried out. As a consequence, one can see that the thresholds sometimes follow, or somehow follow, the Bayesian error. Here. What you can see here is that the Bayesian errors strongly underestimate the values of the real errors. Why? Because they only estimate the uncertainties from the training data, but not the uncertainties of the fitting model. That means you have errors in descriptors, etc. Nevertheless, they capture the trend of the real errors. And the trend is really enough to have a good sampling. It should be also mentioned that we need heating rounds. So from 0 to 800 Kelvin usually means that it goes up because the error increases with increasing temperature. This is required because otherwise the threshold could be stuck at the beginning of the calculations where the force field is bad and the Bayesian estimates are bad, and thus the threshold updates are bad. This would be stuck in too few training samples, resulting in a bad force field. And this kind of plot here, what you see is you will encounter the majority of the times in all systems overall. But there can be exceptions. Here I show you an exception for this is carbon monoxide at a rhodium surface heated from, again, nearly 0 Kelvin to 1000 Kelvin. This is a continuation run of a pure rhodium surface. So we learned first the rhodium surface, then put the CO molecule on it and continued learning. So here, if one would look at the thresholds, you would see that it really behaves differently than the previous calculations here. So I show you the previous calculations here. The thresholds more or less go up stepwise all the time. Here they can go up and down and even have a maximum at 1/4 of the calculation. You also see that before the real errors would be high as before. The real errors are higher than the average, because the average is dominated by rhodium-rhodium interactions, because of you have more rhodium atoms than other atom types. But nevertheless, you see there's a lot of these spikes, of these huge spikes, and these are related to movements of the CO atom, because they result in configurations that are really different than before, have never seen before, and are quite hard to learn. Nevertheless, we would sample here a lot, so we ended up with a lot of training structures and local reference configurations. You see this because this many times you go over this threshold, but the resulting force field was quite good. So I just wanted to give you this as another example of how this learning curve should look alike. So let's wrap up until here what we heard about on-the-fly learning. So first, we need to collect training data in a clever way. Otherwise, it would take too much time to collect it, or it would not collect from the required phase space. For that, VASP offers the on-the-fly training procedure. It uses the Bayesian variances to estimate the errors of the force. The Bayesian errors are usually lower than real errors, because Bayesian errors only estimate the error in the training data, but not in the model, like cutoff radius and descriptors, for example. Nonetheless, this Bayesian estimate is a good estimator, since you only need to capture the trends for a good sampling. And last one should mention for VASP, one should use heating runs for our automatic threshold determination. Otherwise, you can get stuck with too few training data and end up with a bad force field. So from that, we come to some VASP-specific usage of the force field. That means I/O in VASP, how to use it. Here I show the main files of VASP. So let's start with the MLLog file. This is the main output file of the force field. It contains an overview of all important parameters, and it also shows the errors and other analytics at every force field step. For example, the two error plots I have shown you before, they were extracted from the MLLog file. All the information was purely extracted from an MLLog file. And the MLLog file is made in such a format that it is easily grabbable. That means you can write, for example, grep error MLLog file. This would give you the real errors. And you would type this only in the command line. And this, the output would be such that it can be directly used, for example, like in a plotting program, as in GNU-plot. You will later see a small snippet how this output looks like. The next file is the MLAB and /MLABN file. They contain the whole training data and also the local reference configuration list, so which atoms to choose, from which structure, which atom to choose as local reference configurations. The capital N here, but also here's the same, at the end stands for new, and MLABN file is the output file, while the MLAB file is the input file. They are exactly the same, so MLABN can be copied to MLAB to use it later as an input. Next is the MLFFN, MLFF file. It contains the force field, all data in the force field. It is binary, so non-human readable, but to be able to look at how it was created, which parameters, it contains a human readable header. And this header can be really easily accessed from the command line by typing, for example, head -n1 MLFF. Yes, and finally we have the MLReg file. I just wanted to mention this for completion. It contains all the ab initio energies, forces, and stresses listed in one column, and all their predictions listed in another column. This file is not essential at all for any use, but can be interesting if you want to analyze or reproduce or whatever the fitting. Let's come now to the control of the calculations. The control of the machine learning text is entirely done within the INCAR file. All machine learning tags have a prefix ML underscore and then the tag name. So let's start here. I show the most basic, most important files. Let's start with this MLFF. This is the on and off switch, and by setting this parameter to true, the machine learning calculations are enabled. Another essential parameter is this mode. This selects the available execution modes of the code. So in principle, with these two tags, one could already run a machine learning calculation. However, the next two tags are usually also very important to set to really control the calculations, memory usage. These are the MLMB and the MLMconf. The MLMB sets the maximum number of local reference configurations, and the MLMconf sets the maximum number of training structures. So the values of this need to be set, since many arrays that we use are statically allocated once at the beginning of this code. One main reason why we choose this path is this because we also use shared memory, MPI shared memory arrays, and unfortunately found out that the shared memory arrays make really strange behavior and huge problems when they're reallocated. Hence, we wanted to only allocate them only once at the beginning and try to anticipate how large these arrays can grow. So with these 4 tags, more or less, the majority of calculations should work nicely in all operation modes in VASP. But nevertheless, let's talk about some additional control. Let's talk here about the control of the descriptors. More or less, the descriptors is only 2 important tags. These are the cutoff radii for the radial and the cutoff radius for the angular descriptor. So the default values of 8 and 5 angstrom were determined from our experience on many previous calculations and applications. Why these values? Why the value of 8? So why having a bit larger descriptor for the radial descriptor is because it's computationally very cheap, and we saw that by including this, the quality of the force field is significantly improved in some cases. The defaults, as I mentioned, work usually well for most systems. Nevertheless, it's sometimes good to test or optimize the radii, especially the radius of the angular descriptor. So for example, in liquid water, turned out that the radius of 4 angstrom for the angular part is beneficial. Next, we come to some on-the-fly parameters. The first parameter, ML criteria here, selects whether the error threshold is automatically updated or not. No, not means that a constant value is used. Then you have to set this constant value here by MLCTI4, or use this MLCTI4 in a automatic update as the starting value. This default here of 0.002 is a good default that works overall in most systems. A constant value, you would set this to different value, usually as a constant value, if a target force error should be achieved. But I would rather advise this to use this for the more experienced users. And last but not least, I wanted to show you this parameter. There are 2 or 3 others, but I don't want to mention too much. This allows to control how many ab initio calculations are calculated and how many local reference configurations are selected. So by setting this to a higher value, less ab initio calculations are calculated and vice versa. This tag is again more for experienced users, and sometimes if you want to get more accurate force fields than what you have already. Next, we have some important additional training settings. The first three tags here, which start with a W, set the relative weights of the energy, forces, and stresses. Usually setting the weight for the forces has a small impact because we anyway have much more lines for the forces. As I showed you in the example, for example, we had with 500 training structures, 100 atoms each, we have 150,000 lines for the forces and 500 lines only for the energies. And more lines mean that they are weighted automatically more stronger. But what is in most cases can be very important, especially for free energy calculations, is set to increase the weight of the energies, of the total energies. By, for example, increasing this weight by a factor of 10 to 50 or even 100, the accuracy of the energy can be hugely improved immediately by a factor of 2 to 3. While at the same time, this is you have to find usually the sweet spot, but at the same time, almost not affecting the accuracy of the forces and stresses at all. So this should be set at every time if you do free energy calculations, for example. The last parameter here, I just wanted to mention it, that you can also choose the algorithm, but the user usually doesn't have to set this, since this tag is automatically chosen by the ML mode tag, so the tag which selects the algorithm. And usually not all fitting algorithms work with machine learning algorithms together. I just wanted to mention that this is also possible. Next, we come to a very important thing for the on-the-fly learning from MD. You have to set specific MD parameters to make the learning proper. If possible, always use an NPT ensemble with a Langevin thermostat. The NPT involves small volume fluctuations during the learning, and these small volume fluctuations result in much more stable force fields. And the Langevin thermostat is the most ergodic thermostat, which ensures a good sampling from phase space. Also use large enough cells to reduce the volume fluctuations, because you want volume fluctuations, but not too big, because together with, hand in hand with this growth, that you have to increase the energy cutoff by 30%, because due to these volume fluctuations, you can easily get into finite basis set problems or Poulet stress. Increase means that you take the NCAT value that we would use and take a 30% higher NCAT valuing. And also monitor the calculation. For example, if the Brevet vectors increase by more than 10%, stop the calculation, because then you're really likely to, even with the 30% increased energy cut, if you're likely to have a finite basis set problem, that means you just stop it, copy ContCar and MLAB file, so MLABN to MLAB, ContCar to PostCar, and restart the training, and the restarting ensures you have a proper size, basis set size. Then next, for surfaces, keep the box fixed. And last, for liquids, only allow fixed shape volume fluctuations, or only piston-like calculations where you allow fixed two lattice constants, but allow the third lattice constants to fluctuate. This is like a piston. Because I have witnessed myself many times that if you forget this, your calculation runs and the structure distorts into really long rod-like structures, but really long and really thin in one dimension. So you get complete garbage nonsense structures and can throw away this and can restart these calculations. Yeah, so that was everything I wanted to show about these parameters, and let's have a wrap up here. So the main output file is the MLOG file. It contains all the used parameters and the error information at each step. the information is easily accessible using grep on the command line. VASP uses one human-readable file for the training data, the MLAB, or the output MLABN, and one binary file containing the force field, MLFF and MLFFN, but it has a human-readable header to have a look at the parameters. All calculations are controlled via the INCAR file. There are four main INCAR tags: ML, LMLFF, on and off switch, ML mode, which selects the calculation type, MLMB sets the maximum number of local reference configurations, and MLMConf, which sets the maximum number of training structures. Most other parameters, so most parameters are broadly applicable, but there are many other parameters if you want to tweak them. Up to now, there are like, I think at the moment we have 107 parameters that you could tweak. And last, MD calculations involving machine learning force fields need carefully chosen parameters. But many of the stuff, and especially also these parameters, are also mentioned on our VASP wiki, best practices page on the VASP wiki. So from this, I want to come to give you an outline about the machine learning procedures in VASP. So in which order would you do a machine learning calculation, a machine learning problem? First, acquire database via on-the-fly learning. As second, you could optionally reselect the local reference configurations. This step is the go-to step also if you get data from outside and you have no local reference configurations. As third, refit, force field using singular value decomposition. This is automatically set for the refit. We do, as mentioned before, we do this since you get a better accuracy. But as mentioned already before, this is only not done at every step, at the last step, because it's computation much more expensive. And also at this step, we turn on the fast force fields. So the fast execution mode of the force fields. So next is check the accuracy of the force field. A guideline for the root mean square error of the force fields is 5 millieV per atom for the energies and below 100 millieV per atom for the forces. In the next slides, I will come to how to check these errors. If at this point your force field is not accurate enough, you possibly need more training. So for that, repeat previous steps. And as last, as fifth, if you're satisfied, you're okay and can start your actual production calculations with using only the force field. Don't do production calculations within the on-the-fly mode. This is what I can say. So next, we come to the errors, how to check the errors. First, I want to show you that you can divide the errors into two types of errors: training data error and test data error. Let's start with the simpler one, training data error. It is an error of the machine learning force fields compared to the reference data on which the training data was carried out. So the curve, what I showed you before, the black lines in this learning curve were training data errors. It is easily accessible via grep here. You just type grep air ml log file on the command line, and it gives you the root mean square errors. So the output looks like this, and here you have first a header containing the information about this, about the output. This starts always with a hashtag. It's cut here because it didn't have enough space. And then it has the value and D step. So it has the tag name, sorry, not value, tag name, on which ND step this is currently, and the values. So here, root mean square error of the energy, forces, and stresses. On the other hand, you should also calculate training data errors, test data errors, sorry. what are they? So test data errors of the force fields are the error of the force field compared to ab initio calculations on structures which are not directly included in training, but were sampled at similar conditions. This would mean, for example, if you trained until 400 Kelvin, you would not sample structures above 400 Kelvin, but below. But without what I wanted to mention with that similar conditions should be emphasized here, because if you would want to calculate something at different conditions, you would have to extrapolate, and force fields don't extrapolate well. Okay, so comparing to the training data errors, the following is impossible, but this is just theory. We will see that reality is a little bit different. Here, first, test errors are larger than training errors. This means the force field is not accurate enough and more training data should be acquired. Second, test errors are equal to training errors. This is the optimum, but hard to reach. And third, test errors are smaller than training errors. This usually means we have not selected a proper test set, that we have selected too few. Let's say the trained up until 500 Kelvin, and you select a few structures at 50 Kelvin. Yeah, they're really easy to fit, so this doesn't represent a good training set. So you should have errors at least the same usually. So for solids, condition 2, that means test errors equals a training error, is almost fulfilled, but usually it's also a little bit higher. For liquids and molecules, the test errors can be significantly higher than the training errors. And Jörg Behler has discussed in a paper that usually in reality, it's okay to have way higher errors, like a factor 2, 3, 4, or whatever, 5 even. But the rule of thumb is they should be at least of the same order of magnitude. So let's give you an example here. I have calculated this for this talk, only a small example. Cesium lead bromide, 24 atom cell. It was trained between 250 and 400K. I think around 50,000 times. I cannot remember this fully. Not too long, at least, but also not too short. For different temperatures, you see here for different temperatures, I ran then 50,000 time steps with the machine learning force field, so it's fast, and I selected 100 structures evenly. So every 500 structure I took. So I took every 500th structure. Then for those 100 test structures, I carried out an ab initio calculation to have the reference energies and the force field calculation, but I already have the force field calculation, but it doesn't matter, it's so fast. And I calculate the root mean square error of the forces here. So I show here in the plot temperature. So each bar shows the value, and this dotted line shows the training error. So what we see here is that with increasing temperature, the test error increases. This is what I meant. If you have too low, here, for example, this is the force field is definitely good enough, and this is not a good enough test structure. We see that here mostly around 300, maybe up to 350 maybe even, but even here maybe, because we look at the values here, this is 23 millieV per atom, which is quite a good value. The force field is good, but at least until 300 the force field is good. And this means that it is slightly lower a little bit than our end of the heat ramp. So what the takeaway is here, that we should always train at slightly or higher temperatures than our target temperature, where we want to run, where we want to actually get the production runs on. So let's hear another example which shows you that really not everything is black and white. This is molecule ethanol. This is a learning curve for ethanol. That means we show here the evolution of, or the improvement of the force field with increasing the number of training structures. The data was taken from literature. It's a good data, so it was the maximum, it was 1,000 training structures, and also the test data is taken from literature, which are of course different different structures. We see here that here we have the training errors and the test errors. We see that its training errors are more or less converged here, but also the test errors show near convergence. Nevertheless, so this is more or less the best we can achieve. Nevertheless, the force field has a discrepancy of 2.5 or more. So we have a value of 6 millieV per angstrom here, and here 50 millieV per angstrom between the test error and the training error. So we can never reach the training errors the same value. So we have a factor of 2.5 or 3 more. But as mentioned before, the training error, this value is at least at the same order of magnitude as the training errors. So this is still a very good force field with a very low error here of 50 millieV per angstrom. Yeah, so this is what I wanted to show, that it's not always easy to say just by simply looking at the pure numbers of the errors. You have to look at trends, you have to get a feeling, you also have to test it on your production runs, really see if it's bad, and so on. So for that, I want to finish more or less the methodology in VASP and give you some key arguments why to take VASP machine learning force fields. First, as you saw, it's easy to use, very few parameters. In principle, you only need 4 parameters and can tweak all the others if needed. Next, it has on-the-fly training, which automatically extracts the database and reference structures. Next, it's accurate. It's an accurate force field which can typically get you with energy errors below 5 millieV per angstrom and 100 millieV per angstrom for the forces. And this deviation is usually much lower than between different DFT functionals. And next is the efficiency, of course. The execution times are at least 3 to 6 orders of magnitude faster than the DFT calculations. And finally, with this increased efficiency, it allows you to go larger timescale calculations and with structure sizes much larger than in ab initio. Okay, we still have some 10 minutes left. Then I can nicely show you some applications of this force fields. So let's start with this. Here we have popular perovskite methyl ammonium iodide. It's also known as MAPI, so we call it MAPI. And we were interested in the phase diagram of this material. Phase diagram here means that we're interested especially in the temperature-driven phase transition from orthorhombic to tetragonal to cubic. And the phase transition appears in this order from low to high temperature. Let's start with this top left figure here. This shows the lattice constants versus temperature. You see here that in an orthorhombic phase, you would have 3 different lattice constants here. In the tetragonal phase, you would have 2 different lattice constants, and so 2 are the same, 1 is different. And in the cubic, you would have 3 equal lattice constants. And this is how we monitored if the phase transition occurred. This shows force field calculations, and this shows experiment. The first nice thing was that by just running a temperature ramped calculation, we just could observe the phase transformation naturally. This is a big thing because usually if you run an MD, and it's not always the case. For example, I tried with magnesium oxide from the B1 to the B2 phase, never happens. If you want to run MD, that a phase transition, and you want to see the phase transition appear naturally, it's not possible. You will need some kind of advanced molecular dynamic methods. But here, the barrier was possibly so low, the structure sizes were large enough, and the time scale was good enough, large enough, that we could see these phase transitions occur. The next nice thing is, although they miss the actual actual experimental physical values here, and the trend is kept. So you see this is more like a right shift of this curve here, and possibly a big reason why this shift happens is, of course, of electron errors in the electron exchange and correlation. Another nice thing is related to this, we show here again Landau curve, so a fit to Tc minus T to the power of 2 beta. Again, the offset is switched, or the Tc is switched, the Tc value here. But the nice thing is that these Landau parameters are the same for both. So 0.24, beta equals 0.24. Yes, so then this was with the material. So this was a PRL done. This was one of our first papers for the force fields. Another paper I wanted to show you here is the calculation of the chemical potential of lithium fluoride in H2O. For that, we used a specifically modified version of thermodynamic integration, specifically designed to use with force fields, where we can turn off the atomic potential energies here for given atom with a coupling parameter lambda. Then by integrating this coupling parameter from the non-interacting to the fully interacting system here, we can get the chemical potential. So we use this to slowly switch on the interactions of lithium fluoride put into a box of H2O. So in lithium fluoride in liquid H2O. The integrand was very nicely shown, is very nicely shown here. We were very happy that it was so smooth and is nicely integrable. And finally, we got here very good agreement compared with experiments. So this is our final value where we corrected it with a thermodynamic perturbation theory. This is like a first order correction using also some ab initio calculation. Doesn't matter. With this corrected, we are within a few % agreement with experiment. Next, I want to show you here again a phase transition of within solid zirconium. So this shows the phase transition between hexagonal close-packed phase and the body-centered cubic phase. It should be around here, around 1136 K. Again, nice thing is, as shown before for the MAPI, the transition occurs during an MD and it appears naturally. And we saw this by monitoring the whole volume. And you see this by a jump of the volume here, by a abrupt jump. And here you would also see it, but this red curve lies over the black one. The other nice thing is it's also reversible, although showing some hysteresis. And finally, within this 100 atom 8 cell with using scan, we could get within 10% of the experiments here. So for the heating, for this heating run, we could get this 1046K compared to 1136K with experiment. Yeah. And in chronological order, the newest one, I want to show you some results on delta learning in zirconium oxide. So let me tell you in advance what the purpose of this method is. It is to be able to train a force field on higher level electronic methods such as RPA, but without the need to perform ab initio calculations on the whole training data with that method. So, but let me explain how. So first we train here a force field we used for the 96 atoms. It's a medium-sized cell. And we got 592 training structures. We would denote this as QML, so quantum mechanical calculation of low quality, because we used for this PBE. The second is we took a small cell with 24 atoms. It was slightly elongated to capture some van der Waals interactions, doesn't matter, but the point is much smaller cell. Okay, we ended up with 1270 structures. We rank compressed them. This doesn't matter. The important thing is we ended up with 168 structures, much less than here. And we used this 168 small structures to get the difference between high-level quantum mechanic calculation and the low-level quantum mechanic calculation. That means we carried out for them RPA calculations for energies and forces, and the stresses we got by finite difference. This is not implemented in VASP, but you could leave away stresses also. And with that, we use this energy differences as the energies and the force differences as the quantities to learn. So we trained a force field that can predict differences. We trained this force field on 24 atoms to predict differences on any size of structures. And then we applied this force field to the originally 592 structures with 96 atoms to predict all the differences, all the energy and force differences in these structures, and added those differences to the low-level quantum mechanic values. After that, we took these new energies, forces, and stresses here and used them as input to train the final force field, which we tag here quantum QM high with a delta here. So this has, in principle, this should be the same as if you would train on RPA, the whole big data you would train on RPA. And the error between these two should be really small. For the forces, it is around 1 to 2 milliV per angstrom. This, I also show you here some validation of these force fields. You see that so we did, to validate this, we did this on scan. So we can do the whole procedure instead of RPA here, we use scan. And in that case, you can also, but scan it, because scan is cheap enough, you could just run the whole calculation, this one here, with 592 structures with scan, and compare the value from the real trained to the delta trained, and you see the agreement is almost identical. So here, this curve and this curve, this shows free energy differences, and this again, a Landau plot. And last but not least, to conclude my talk, we then used it to predict the phase transitions between monoclinic to tetragonal and tetragonal to cubic zirconium dioxide, so zirconia. And we saw that although RPA gives here a better value, does not change much here, or gives only a slight improvement above scan, but this was anticipated from previous literature results. But what we saw here is that we could first establish, so make this methodology run in VASP. It's important also to mention this methodology was not our idea. This was already proposed in 2015, but we made with this paper the first time to run it in VASP. Okay, that's the end of my talk, and thank you for your patience, and feel free to ask questions.
Thank you very much, Ferenc. Yep. Fantastic. So one can really see how you know these algorithms inside out. So let's immediately jump into the Q&A, because there are many questions. I will read them out from the Q&A window. Yeah. So some of them were asked very early in the talk, but I think they are very relevant. So can one use machine learning in t=0 calculations to have a fast relaxation calculation step instead of doing an ab initio?
Yes, this is a yes. This we do. You can, in principle, you can use every method in VASP where you need forces. You can train the force field and then use that force field for that method. I think we have more or less everything works. So we had small bugs. So in principle, everything should work out of the box, but we had some bugs in the main loop. But I think now even iBrian 5 and 6 works. This means iBrian 5 and 6 are finite differences for phonons. So you can use this for relaxation phonons and molecular dynamics.
So there it really makes sense to use the latest version and have an eye on the known issues, perhaps on the wiki.
Yes.
How does DFT not give the energy per atom? So is it, I think that was right at the beginning when you talked about the assumptions by taken for MLFF. Maybe you can explain that decomposition again.
Here. Now, this is just a pure assumption we do, because if you look at the energy from the Kohn-Shamick, so for the total energy in DFT, you see there's many contributions, and you don't have a per se really per atom contribution there, like here. You cannot split up observables in DFT into per atom observables so easily. This is also true for other things.
Yes, so maybe we can discuss
this is just a pure assumption we do, and there's no proof for this. We hope that this just we just assume this, and this has worked out well until now. It's not done by us, it's done by more or less everyone in the machine learning community. But just to mention that this is just an assumption.
Yes. So will the accuracy of an MLFF depend on the atomic environment cutoff radius used, and should we check for convergence with respect to that cutoff radius?
Yes, we come here. What was this? In principle, as I told you, it's very often not worth it at the first look. Only if you want to so here, for example, I had liquid water as an example. This is really for a special case, because we saw that it only needs 4 angstrom cutoff to really achieve high accuracy, for going from 30 millieV per angstrom to 24 millieV per angstrom. Because why I mentioned this, because Georg Gresse was really doing a ton of calculations on this, on water. This is his tool playground, more or less, to play on H2O. Usually you're really fine with these standards here.
Yeah, so this is just for fine-tuning some hyperparameter
really for
optimization.
Yes.
So
it
it's
really
not
depends
really
on the
a
case,
convergence study with respect to that. So you wouldn't continuously increase it and then it becomes continuously better. But
no,
here in this case, having a smaller cutoff radius is better than the default 5.
Because it makes fittings. So the reason why it doesn't get better with increasing radius is because you would need more training data and so on also. So just by refitting with this, but because we usually don't do another on-the-fly training, but we just refit. And sometimes the more the radius is, the harder it is to fit. So you can just simplify stuff by going to 4 angstrom, and anyway, you capture majority here with this 8 angstrom. So capture majority of interactions with 8 angstrom. So already a pure two-body descriptor would give you like a 70% good force field or whatever, 80%.
Okay, then a question about the kernel function. So what is the unit of x in the kernel function?
Because it's normalized.
Yeah, so there is no unit on that. Which kind of environments are considered to be identical? Okay, so that is coming back to the definition of descriptors, right? So
yeah, but let's say, for example, I mean, I think here what you see is that if you, for example, run a high temperature like 800 Kelvin, then if you have no phase transition, let's say up to 100 Kelvin, in this region of 100 to 800 Kelvin, the 800 Kelvin calculation in an MD contains all structures of lower temperature too, but with different probabilities. That means you want to just...
It might be that Yes, so this is about the ensemble, and also quite important to stress which configurations and local environments will be included in some simulation. But I think this is more a question about how is the vector x constructed. So how can you say that two?
It's the coefficients of the descriptors. So it's just this x is the first whatever are the radial descriptor coefficients. So these coefficients here. So sorry, this coefficient, this p, this is the angular, and these c's are the coefficients of the radial, and the x is just a collection of these coefficients.
Mm-hmm. Yes,
And
I think this.
Okay, and the indices, if you're interested, are so n is the number of radial functions that you set as a parameter, and nu is another number of radial functions because you have here n and nu, or n and n prime. L is the like an angular quantum number, and here you additionally to this I, you would have j and j prime, which are the types, two types. So it's case quadratically with a number of types. I haven't shown this because of simplicity. So these coefficients measure the probability of that configuration, more or less. And you measure with this overlap, you measure the probabilities of two configurations.
Yes, thank you. So let's continue with the next question. It's about how to train. So does this mean that we should only create force fields on heating, and once created at a constant temperatures might be unreliable? Yeah. So on-the-fly machine learning is not possible for constant temperature MD simulations?
Let me show you that. So what happens if you have bad luck, if you have constant temperature? If you have constant temperature, so if you start an MD, at the beginning your force field is bad because you don't have enough data set and local reference configurations. At that point, of course, you get an ab initio calculation, it fits. Then the next 5 steps, it's the same. But after, let's say, from the 10 steps on, you already have some kind of a force field that can be below a threshold, because the threshold, as I showed you, is calculated as the mean of the last 10 Bayesian errors. So in the first 10 steps, we had very bad Bayesian errors because our force field is bad. So this can be, sometimes this can be by accident too high. And from that point on, your force field would say, okay, I'm below this, although because the threshold is garbage.
So starting at low temperatures, make sure that you first pick up very representative local configurations.
Not at all.
Then...
Now the idea is that the simple idea is, but it works like 98% of the time, 2% you have bad luck, is that the idea is that by increasing the temperature, you have more motion, and the likelihood that you're really wrong is higher. And with that, you could still, with this so you had a constant update of the threshold at a low temperature, and if you would stay at that temperature, all your motions would be too small that you go below this wrong threshold, and you would never pick up new training structures. But since you heat up, you move so much that you still get somehow above this, and then a new update is, but the next update is already much better, and so on, and then it repairs itself. So this is like
a good warm-up phase for the...
It's not it's not that super stable algorithm, but we could not come up with something better until now. An alternative to that, you can run constant temperature calculations if you have a constant threshold, if you know what your threshold should be, but this is then not automatic so easily. Then you have to know a little bit about the system to set this to what value. Georg,
and especially if you trained on a heating run, what does this mean for applying this force field at a constant temperature?
Yeah, so if you have no phase transition in the heating, that you should be careful. If you encounter some phase transition and don't want to learn that phase, should not include that, because that gives a lot of additional information, which is making the force field too universal is not good, because with that you increase the variance of the force field and your errors get higher. But it means that, as I told you, that if you have, for example, between 800 and 100 Kelvin and you have no phase transition, and you train up to 800 Kelvin, it contains all the structures up till 800. But I think it will be not a reliable force field as in 800, as you can see here. So this, where is it? So here you can see this nicely. If I would, for example, want to have a force field 400, I would possibly train here from 350 to 500. Problem solved. The problem is, if you wanted at 400, there's a phase transition, but then you take the phase transition inside. That's another problem. So there's no phase transition. I mean, here could be a phase transition. Yeah, it was a fast example. It's a dangerous example. It's a fast example here. I had to create something for this talk, this figure. But
no, I think this was already very useful comments there. Can I
takeaway is that just train above the target temperature. This is the takeaway.
Yes, that is a good takeaway.
Yeah.
And now a bit of a question about the versions. I think we cut on that already. In VASP 5.4, is there on-the-fly training included in that version, or only newer versions?
No. It came,
and
I think,
the active. Sorry.
It's 6.40. It came, so the active learning was from the beginning or thereon. So when machine learning came, it was inside, but when did we release machine learning? 6.3 or 4? Sorry, I can't tell you this now. It should be around 6.3 or 4 where we released machine learning, I think.
Yes. And I think one newer maybe that might be confusing. There's this ML mode tag that was only introduced in the latest, or
no, it's also around 6.3 or 4. It came with the fast force fields, I think.
Okay. Yeah. So, but this is usually documented on the VASP Wiki page.
Yeah, it's documented the VASP Wiki and the releases page. Yes.
And with this very new features, it makes a lot of sense to keep up to date with the latest version of VASP.
Simple as to say, VASP 5 doesn't have it. VASP 6 above has it. So if you buy VASP 6 above, you will have it. And you always use the latest version. This is what I can tell everybody to this. Don't try to see, this has this feature, this. Now, the latest is the best.
Then maybe let's close with one more question that is very aiming towards molecular dynamics, because that is also what we will discuss in the hands-on today. So I'm reading out loud. In my experience with building models using the VASP MLFF, I've noticed that dynamic parameters such as the Legeveur gamma setting in the training phase seems to impact the result, possibly influencing the final MLFF parameters. Is it true that the MLFF parameters might inherit characteristics from the dynamic settings like the Legeveur gamma or PMAS? And if so, how should I approach the selection of the dynamic parameters during the training? Should it be the ones that are optimal for an ab initio molecular dynamics calculation, or is there some other strategy?
I think it's not that problematic. To be honest, you get different trajectories maybe, but the trajectory you have to. I mean, what you have to check: on average, did you conserve, for example, the pressure or the temperature in your trajectory? If that is done, then it's okay. And I mean, there's some ways how to select this Langevin gamma and gamma L, but I saw that usually with a value of 5.0, you're well. Yeah. So I would not make. I mean, I would just check within this calculations have the quantities that need to be conserved, like for example, if you run an NVE, for example, energy or the pressure in an NPT or temperature on average. You have to build the average, of course, and you have to see that there's a relaxing phase, the relaxation phase, and of course, if phase transitions occur, everything can happen. So that you can have some kind of relaxation times in the phase transitions occur.
Yes.
If you want to make really sure, just run a quick on the fly relaxation up to some 10,000 steps, throw it away, and start from scratch with that new concat. This you can also do.
So basically, running all the kind of tests that you would run on a molecular dynamics simulation in order to check whether this is a good
exactly.
MD trajectory.
The molecular dynamics has to be correct, otherwise you're screwed.
Okay, fantastic. So thank you very much for answering so many questions. See you in a bit. Thank you.
Thank you. Bye.
Time for questions in our Q&A session. Thank you very much.